Hi everyone, this video is on question 2 of exercise 9i from PO2. So we have the function f of x is arcsine x, and in part A we want to show that the function is concave on the interval -1, 0. So a function is concave when its second derivative is less than or equal to 0 for certain value. So if that happens, then we say this function is concave for the intervals x to y, for example. And a function is also convex if its second derivative is greater or equal to 0 for a certain interval. Now, in this case, if you want to show if it's concave or convex, we first need to find the second derivative. So f dash x is equal to, I'm just going to use the standard results. In previous videos, I have shown how you can directly differentiate arcsine x. But for the interest of time, I'm just going to use the standard result that arcsine x, the derivative of arcsine x, is 1 over square root of 1 minus x squared. Now, this is the derivative of arcsine x, and we need to differentiate this again. But before that, I'm going to write this in a nicer form, because this can be written as 1 minus x squared to the power of minus a half. Now, f double dash x is equal to, so we use the chain rule to differentiate this, minus 1 over 2 comes down, and also from inside the function, the derivative is minus 2x, and then we write down the function, and then we have the power minus 1, which is minus 3 over 2. And we can simplify this, which becomes x over 1 minus x squared to the power of 3 over 2. So this is the second derivative, and now we are at a position to find out if the function is concave and also convex in the next part. So here the interval that we are considering is the interval -1, 0. And if you consider the behavior of the second derivative in the interval -1, 0, remember that in the interval -1, 0, all the x values are negative. So in the interval -1, 0, all the x values are less than 0, which means they are negative. And now we can just analyze the behavior of this function when x is negative. So if x is negative, what's going to happen here is that the numerator is always negative. Then the denominator, what's going to happen in denominator is that, so you get a positive number, so because it's x squared, so you get a positive number in the denominator. I mean, when you square that, but you have 1 minus that. So this one is important to realize, because here what's happening is that because we want to see, is it overall going to be positive or negative? X squared is going to be a positive number, okay, but then we have 1 minus that positive number. If that positive number is greater than 1, then the denominator is going to be negative. If that's less than 1, the denominator is going to be positive. Now, the key is that x is between -1 and 0, so which means it's a number that is less than, its magnitude is less than 1. So it's like a half or a third, and when you square those numbers that its magnitude is less than 1, then the square of that is actually going to be smaller than that number itself. For example, half a squared is a quarter, and a quarter is less than half. So this simply means that x squared is always going to be a number that is less than +1. So when you do 1 minus that number, you get a positive number in the denominator overall. And as a result of that, the entire thing is going to be negative. And since the entire number is always negative, which means that the second derivative is always less than or equal to 0 in the interval -1, 0. So that's basically the answer. So I know I explained lots of stuff, but in order to answer this, you can just mention some of those facts, such as in the interval, the denominator is always positive, the numerator is negative, so the overall sign is going to be negative, and that's why this number is always less than or equal to 0, which means the function is concave as a result of that. Okay, now we can do part B. So in part B, we need to show that the function is convex on the interval 0, 1. So the interval this time is this, x is between 0 and 1. So again, it's just all about analyzing the behavior of the function in this interval. So the second derivative is x over 1 minus x squared 3 over 2, and a function is convex when f double dash x is greater or equal to 0. So in this interval, again, any number that we have is less than 1 between 0 and 1, which means a square is going to be less than that number. Okay, so the numerator is always positive. That's very clear. The denominator, so if you square half, for example, you get a smaller number, and always the denominator is 1 minus the square, which is still a positive number because that number isn't greater than 1. So your denominator is also always positive. So as a result of that, you get a positive number all the time in the interval x is between 0 and 1. So we can conclude that the second derivative is always greater or equal to 0. So it's convex. The function is convex. Okay, now part C, which is basically finding the point of inflection of f. So if you want to find the point of inflection of a function, there are two conditions that must be satisfied. So the first condition is the more straightforward one, is that we have to solve this equation f double dash x, sorry, not 0 here, I just meant f double dash x is equal to 0. So this is the first equation that we need to solve. And by solving this, we'll get a value for x, and then we use that value of x to check the second condition. If the second condition is satisfied, then we can conclude that that's the point of inflection. Of course, we need to then substitute the value of x into the function to get the y coordinate, but I'm going to show you how. In this case, we first are going to use f double dash x. So f double dash x has the equation x over 1 minus x squared to the power of 3 over 2 is equal to 0. So we want to solve this equation. So it's a simple cross multiplication which gives us 0 for the value of x. Okay, now we know this. This was the first condition. The first condition is just solving this equation, and we want the equation to have a solution at least, right? We don't want sometimes, because it's possible to don't get any solutions. So yeah, now we have a solution for the value of x. The next step is the second condition to check if it's a point of inflection. How can we do that? It's basically about analyzing the behavior of f double dash x just before and after the value of x. So what I mean is that we can first check the behavior just slightly after this value of x is equal to 0, just by adding a very small amount, like 0.1, for example, to x value. And the second step is checking just before that by subtracting a small amount. And then we are going to just find these values by substituting into the f double dash x equation. And what we are hoping to get is to get two numbers with opposite signs. So one of them must be positive and the other one negative, because if that's the case, then that means the curve changes from being concave to convex after the point of inflection, or vice versa. And that's exactly what we want, because if we get two positive or two negative numbers, then that means that hasn't happened. So the function remained concave or convex, and that means that's not a point of inflection. So now it's all about substituting this into a calculator, by using calculator, substituting into the function, and see what we get. So f double dash x of 0.1 is equal to 0.102 to 3 decimal places, and for minus 0.1 it's minus 0.102, and this is exactly what we wanted. We wanted to have two opposite sides. And since now this is the case, we can conclude that indeed when x is equal to 0, that's the x coordinate of the point of inflection. Because remember, we need to find the y coordinate. So in order to find the y coordinate, we just find f of 0. So we just find arc sine 0. Which is 0. So the point of inflection has coordinates 0, 0, and that's the origin. So this is the coordinates of point of inflection. So thus 0, 0 is the point of inflection after all these steps. So yeah. Okay, that's it for this video, and thank you for watching.